So we're well into 2025, and it's become clearer than ever that the pace of digital transformation isn't just fast, it's accelerating at an almost unbelievable rate. Everything we do, from how we work to how we connect, is being reshaped by technology. And at the very heart of this digital explosion, the unsung hero quietly powering it all is the server. For a long time, server tech felt like it was moving at a steady, predictable pace. But this year, that's completely changed. We're seeing some truly landmark innovations that are redefining what's possible in data centers and beyond. These aren't just minor tweaks or incremental updates. We're talking about fundamental shifts in architecture, cooling, and management that are making servers more powerful, more efficient, and more intelligent than ever before. This is the kind of stuff that enables the next generation of AI, IoT, and cloud services. It's the foundation upon which the future is being built, and the changes happening right now are setting the stage for the next decade of tech. The ripple effects of these advancements will be felt across every single industry. It's a genuinely exciting time to be following this space, whether you're a seasoned IT pro, a developer, or just someone curious about the tech that powers our digital world. The game is changing, and the new rules are being written as we speak. So I figured it was the perfect time to break it all down. Let's dive into the top server tech trends that are revolutionizing the industry this year. Alright, first up, let's talk about something that's been brewing for a while, but has finally hit a major tipping point in 2025, ARM-based servers. For the longest time, if you thought about the chip inside a server, you were almost certainly thinking about x86 architecture from Intel or AMD. ARM, on the other hand, was the king of mobile. Your smartphone, your tablet, pretty much any low-power, high-efficiency device was running on an ARM chip. The consensus was that ARM was great for battery life, but it didn't have the raw horsepower needed for serious server workloads. Well, that narrative has been completely flipped on its head. The performance per watt of modern ARM-based server processors is just incredible. Companies like Ampere, and even cloud giants like AWS with their Graviton chips, have been pushing the boundaries of what these architectures can do. They've proven that you can get massive core counts and impressive performance while consuming significantly less power than their traditional x86 counterparts. This isn't just a niche play anymore for specific lightweight tasks. We're seeing ARM servers being deployed for general-purpose computing, web hosting, databases, and even some high-performance computing applications. The energy savings alone are a massive draw for data centers where electricity costs are a huge operational expense. What this means is that the server CPU market is more competitive and more interesting than it has been in decades. This competition is driving innovation across the board. It's forcing everyone to get better, more efficient, and more specialized. For consumers of cloud services and businesses running their own data centers, this translates to more choice, better performance, and lower costs. The move of ARM from the pocket to the data center rack isn't just a trend. It's a fundamental restructuring of the server landscape, and it's happening right now. Next up is a concept that's moving from the buzzword category to a real-world, critical piece of infrastructure edge computing. The traditional model was simple. All your data goes from your device to a massive, centralized cloud data center for processing, and then the result comes back. This works fine for a lot of things, but what happens when you need an answer instantly? When even a fraction of a second of delay, or latency, is a huge problem? That's where the edge comes in. Instead of sending data on a long round trip, edge computing uses smaller, localized servers to process data right where it's created. Think about industries where real-time decisions are a matter of life and death, or at least critical for operation. Autonomous vehicles, for example, can't afford to wait for a signal to go to the cloud and back to decide whether to brake. A smart factory needs to detect a manufacturing flaw on the assembly line in milliseconds. In healthcare, remote patient monitoring devices need to analyze vital signs and alert doctors immediately if there's an issue. Edge servers make this possible by bringing the compute power closer to the source, drastically reducing latency, and also improving security by keeping sensitive data local instead of sending it over the public internet. So in 2025, we're seeing a massive build-out of this edge infrastructure. It's not about replacing the cloud, it's about extending it. These edge servers might be in a cell tower, a factory floor, a retail store, or a hospital. They are becoming the essential middle layer that connects our billions of IoT devices to the powerful analytics and storage of the central cloud. This shift is creating a more responsive, resilient, and secure digital world. and it's fundamentally changing how we design applications and infrastructure for a connected future. For as long as we've had powerful computers, we've had to deal with the heat they generate. And for decades, the solution in data centers has been pretty straightforward: blast them with cold air. Huge computer room air conditioners, or CRAC units, would chill the air, which would then be pushed through raised floors and pulled through server racks by dozens of tiny, screaming fans. But as servers get more and more powerful and densely packed, we're hitting the physical limits of what air cooling can do. The latest CPUs and GPUs generate so much heat that air simply can't remove it efficiently enough. This is where liquid cooling steps in to become the new standard. Now, liquid cooling isn't a brand new idea. PC enthusiasts have been using it for years, but deploying it at data center scale is a different beast entirely. In 2025, we're seeing two main approaches go mainstream. The first is direct-to-chip cooling, where small tubes deliver a coolant like water or a dielectric fluid directly to a cold plate sitting on top of the hottest components, like the CPU and GPU. The liquid absorbs the heat much more effectively than air and carries it away to be cooled. The other, more extreme method is full immersion cooling, where entire servers are submerged in a non-conductive, thermally efficient fluid. It looks wild, but it's incredibly effective. The benefits here are huge. Liquid cooling allows for much higher density server racks, meaning you can pack more compute power into the same physical space. But the biggest win is energy efficiency. You're eliminating the need for those massive, power-hungry CRAC units and all those server fans. This dramatically reduces the data center's overall energy consumption, which not only saves a ton of money on electricity bills, but also has a major positive impact on sustainability goals. What was once a niche solution for supercomputers is now becoming the norm for high-performance data centers. So, we've got these incredibly powerful and efficient servers, but how do you actually manage a fleet of thousands or even millions of them? The complexity is just, honestly, beyond human scale. That's why one of the most impactful trends of 2025 is the deep integration of artificial intelligence into server and data center management. We're moving away from reactive problem solving, where an admin gets an alert that something has already broken, to a proactive and predictive model powered by AI. It's really about letting the machines manage themselves to a large extent. Imagine an AI system that constantly monitors the health of every component in every server. It analyzes performance metrics, temperature, vibration, and power usage, learning the normal operating baseline. By spotting tiny deviations from that norm, it can predict when a component, like a hard drive or a memory module, is likely to fail, and it can do so weeks in advance. This allows for predictive maintenance, where the part can be replaced during a scheduled window before it ever causes an outage. This alone is, honestly, a game changer for uptime and reliability, minimizing unexpected downtime that can cost businesses millions. But it goes way beyond just predicting failures. AI is also being used for real-time optimization. It can automatically perform load balancing, intelligently shifting workloads between servers to prevent bottlenecks and ensure smooth performance. It can optimize power consumption by dynamically scaling resources up or down based on demand, or even adjust cooling systems in real time to target hotspots. This level of automation and intelligence not only boosts efficiency and reliability, but also frees up human IT professionals to focus on more strategic, high-level tasks instead of constantly firefighting. AI isn't just a workload running on the servers, it's becoming the brain that runs the data center itself. Let's switch gears a bit from hardware to how we actually use it. The next big trend is the massive adoption of serverless architectures. Now, the name serverless is a little bit of a misnomer because, of course, there are still servers involved. You can't escape physics. The key difference is that as a developer, you no longer have to think about them. You don't have to provision servers, manage operating systems, patch security vulnerabilities, or worry about scaling them up or down. You just write your code in the form of functions and upload it to a cloud platform like AWS Lambda, Azure Functions, or Google Cloud Functions. The cloud provider handles everything else behind the scenes. When your function needs to run in response to an event, like a user uploading a photo or making a purchase, the platform instantly spins up the necessary compute resources to execute your code, and then spins them right back down when it's done. You only pay for the exact compute time you use, down to the millisecond. If 1,000 users hit your app at once, the platform automatically scales to handle 1,000 concurrent executions of your function without you having to lift a finger. This is a massive departure from the old model of provisioning a server and letting it sit idle most of the time, just in case you get a spike in traffic. The benefits for developers and businesses are profound. It leads to incredible agility. You can build and deploy new features and applications faster than ever before. The cost savings can be significant, as you're no longer paying for idle server capacity, and the automatic scaling provides a level of elasticity that's very difficult and expensive to build yourself. While it's not the right fit for every single workload, serverless is becoming the default choice for event-driven applications, microservices, and any task that has variable or unpredictable traffic patterns. It represents a fundamental shift in how we think about deploying software in the cloud. This next trend, composable infrastructure, is all about treating your data center hardware less like a set of rigid, pre-configured boxes, and more like a fluid pool of resources. In a traditional setup, a server is a self-contained unit. It has a certain amount of CPU, a certain amount of memory, some storage, and a network card, all locked together in one chassis. If you have an application that needs a ton of memory but not much CPU, you still have to buy the whole server, and that expensive CPU might sit mostly idle. It's an inefficient way to allocate resources. Composable infrastructure completely breaks down that model. It disaggregates the core components, compute, storage, and networking, into separate pools. Imagine racks filled with nothing but CPUs, racks of just memory, shelves of storage drives, and pools of network fabric. Then using software, you can compose a server on the fly, pulling the exact amount of each resource you need for a specific workload. Need a server with 8 CPU cores, 1 terabyte of RAM, and 50 terabytes of fast storage. The management software programmatically assembles that virtual server for you from the available pools. When that workload is finished, the resources are decomposed and returned to the pools, ready to be used for the next task. This provides an incredible level of flexibility and efficiency. It dramatically improves resource utilization because you're no longer over-provisioning or leaving expensive hardware sitting idle. It also simplifies management, allowing administrators to provision and re-provision infrastructure in minutes through code, a concept known as infrastructure as code, or IAC. This is the ultimate expression of a software-defined data center, giving businesses the cloud-like agility and efficiency within their own private infrastructure. Finally, and this might be the most important trend of all, is the intense focus on sustainability. For a long time, the primary goals in server and data center design were performance and reliability, with efficiency being a secondary concern mainly tied to cost. In 2025, sustainability is no longer an afterthought. It's a core design principle and a major competitive advantage. The sheer energy consumption of the world's data centers is staggering, and with the explosive growth of AI and data-intensive workloads, that demand is only going up. The industry has recognized that this growth has to be managed responsibly. This focus manifests in several key ways. We've already talked about some of them, like the move to hyper-efficient ARM-based servers and the energy savings from liquid cooling. But it goes much further. Data center operators are making massive investments in renewable energy, building huge solar and wind farms to power their facilities, or signing long-term power purchase agreements to ensure their electricity comes from green sources. There's also a huge push in designing data centers to be more efficient from the ground up, optimizing airflow, using free cooling in colder climates, and even finding ways to recycle the waste heat generated by servers to warm nearby buildings. Beyond just energy, there's a growing emphasis on the entire life cycle of the hardware. This includes using recycled materials in server construction, designing components for easier repair and refurbishment, and establishing responsible e-waste recycling programs. Companies are now being measured and judged not just on their uptime or their profits, but on their carbon footprint and their overall environmental impact. Sustainability has become a critical pillar of modern server technology, driving innovation that's not just good for business, but essential for the planet. So, from the efficiency of ARM and liquid cooling, to the intelligence of AI management, and the flexibility of serverless and composable systems, it's clear that 2025 is a landmark year for server technology. These aren't just isolated trends, they are interconnected pieces of a larger puzzle. They work together to create a foundation for computing that is more powerful, more agile, more intelligent, and crucially, more sustainable than ever before. This is the hardware and architecture that will power the next wave of innovation we'll see in our daily lives. These advancements are what enable more powerful AI models, more responsive and immersive virtual worlds, and breakthroughs in scientific research. The future of server technology is about creating an infrastructure that is almost invisible, a seamless, scalable, and intelligent fabric that developers and businesses can build upon without being constrained by the physical limitations of the past. It's an exciting evolution, moving from rigid boxes to fluid, software-defined resources that can adapt to any need. The pace of change in this industry is only going to continue to accelerate. What feels cutting edge today will be the standard tomorrow. So it's more important than ever to keep an eye on this space, to stay curious, and to understand the forces shaping our digital future. Thanks for watching, and I'll catch you in the next one.